in contact with the environment for a certain amount of time. In general, all of these pure states will evolve into mixtures. Now you can assign to this mixture a number, an entropy of that final density matrix. This entropy will tell you how much the system got entangled with the environment. If the entropy is 0, it didn't get entangled. So we will look for states which are as little entangled as possible. In other words, if I think of it, I mean, this is a multi-dimensional Hilbert space, but I'm trying to represent it on a two-dimensional screen. I'm looking for a peak with entropy near the peak being 0, and most of the states will have high entropy and will be bad ones. They will decohere. So I think that probably answers your question.
How do you select the basis?
You don't select the basis. You let the interaction select preferred states. Right?
So you have selected a basis by
Which one?
defining alpha, by defining your 0 and 1 of your two-state system.
So if I were to do this strategy here, I would pick a random basis, I mean orthogonal for convenience, turn on the interaction, and look for states which are not damaged. Right? So interaction tells me what are the states which are not damaged.
Magnetic field will do it.
Magnetic field won't do it. Magnetic field will just rotate things.
No, it will still be 0 high.
There is not going to be entanglement between magnetic field and the spin. That's a key. Okay, so the entropy of the spin is going to stay the same. It can introduce a phase which you can think of as random if you don't know the field, but it's not going to change the purity of the entropy of the system. Anything else? Question?
But it sort of seems like an overkill to insist on the full state being undisturbed by the environment when we are only observing certain amount of stuff, like your body, we observe the coarse-grained aspects of it, but not the microscope.
Excellent question. I'm going to postpone it. Okay? I'm doing sort of foundational introductory stuff, right? So I'm not going to address it. But it's an excellent question. It's very clear that if I have states which are very near each other, I will not be able to tell the difference, and environment also will not be able to tell the difference as well. Okay? So, in fact, at some point, just to go a little bit along these lines, we define something as a quantum halo around puncture states, right? You can deform them a little bit, and they won't lose predictability as badly, right? But then, yeah. Nothing urgent at the moment. Okay. So often, because entropy is painful to calculate, because you have to diagonal matrices, one can use trace row square, which is so-called Renyi entropy or purity, right? And in this case, the purer the state, the bigger trace row square. Again, predictability is it. You want to look for states which are predictable. Entropy doesn't increase, purity doesn't get lost. You are not guaranteed you're going to find them. There are environments with coupling such that you won't get anything good. Well, I think enough. So, states that entangle least with the environment are the ones which are candidates for classical states. Let me look at a very simple example which goes beyond our spin interacting with a bunch of other spins, and which is sort of, in some ways, more realistic, but still exactly solvable. A harmonic oscillator interacting with a bunch of harmonic oscillators. Here I'm saying field, but field is really a bunch of harmonic oscillators. The interaction Hamiltonian, this is some coupling constant, is proportional to the position of that harmonic oscillator. That's important. Interactions typically depend on how far things are from each other. And this ends up determining the fact that things are local. that they prefer to be in a well-defined position. Because the whole system is linear, you can solve it. You can obtain effective equation of motion for the density matrix of the harmonic oscillator. So, you know, you can even obtain exact solution of the whole problem and trace out the field and then do things. And if you did it, you get an exact equation which looks nasty. I'm going to write it in the case where it loses a couple of its terms, which are not crucial for what we want to discuss. This equation is written here in position representation. So this is a derivative of a density matrix. And I've retained the terms which are dominant and which you can recognize. The first term is a von Neumann product. This is shown in the equation. The second term corresponds to relaxation or damping. If you look for the quantum limit, for the classical limit of quantum, then one can do the following mathematical trick, which is physically illegal. Let h bar become smaller than it would be. And look which terms will dominate in this case, right? Small h bar is where you look for classicality. Well, here you see that from the terms on the right-hand side, h bar squared appears in denominator here. So this will blow up as h bar goes down. So clearly this term is important, and it turns out this term really dominates decoherence. Moreover, with this insight in mind, let us drop for now these other two terms and just see what happens if we have an equation saying rho dot equals this. Right? This equation can be solved. And the solution is down there. It simply says that whatever you had initially as a density matrix is going to be modified in such a way that when x is equal to x prime, on the diagonal, nothing happens because x minus x prime is 0. However, away from the diagonal, you're going to dump at a rate given by this and proportionally to how far or how long you wait. In other words, if you have a situation you would expect in a double slit experiment, a superposition of something being here and there, the initial density matrix in position representation will have two peaks on the diagonal. They correspond to possible location of the particle, but then it will also have two peaks of equal height away from the diagonal, and they contain information about the coherence between the two peaks on the diagonal. The equation we've had before is going to leave the peaks on the diagonal untouched, but is going to diminish the peaks away from the diagonal. This is how coherence gets lost. You end up with either here or there. Question, of course, how quickly does it happen? And for this we can come back to the equation. Turns out, for this equation, you can express decoherence rate, the rate at which off-diagonal terms get depleted, in terms of how quickly energy or momentum get lost from the system. So gamma is damping coefficient. Decoherence rate is given by gamma times something. Now, if it's given by gamma, that means that if you isolate your system extremely well from the environment, you would think you would be able to preserve coherence. Well, you would have to be really good in isolating this, because this term is the distance, the size of the superposition, distance between the peaks, divided by lambda de Broglie wavelengths, thermal de Broglie wavelengths. Thermal, because the equations that I wrote before assumes temperature is dominant in Duffy. So, for example, if I were to assume that I can isolate my system so well that gamma corresponds to Hubble time, age of the universe. So 10 to the 17 seconds is how long you can maintain coherence in the system. If I were to take delta x to be 1 centimeter, macroscopic but not huge, mass to be 1 gram, macroscopic but not huge, and temperature to be room temperature, then this is 10 to the 40. In other words, if I can isolate the system so well that it loses half its energy only over a Hubble time, it's going to lose its coherence over 10 to the minus 23rd second. Decoherence is exceedingly effective. Now, when you have a real system and when you run into numbers like 10 to the 40 and so on, you better look whether there are no cutoffs and problems and whether you are not, I don't know, above Planck energy or something like that. And sometimes you will be, but I think the basic conclusion, decoherence is very effective, is going to stand. Any other questions at this point? Question?
Are you, in this statement, you're distinguishing it from line selections?
So in this statement, so the two come together, right? Here I've set up superposition and I looked at how quickly it's going to lose coherence. Right? I can ask the question about preferred basis, and it has a well-defined answer, which depends in an interesting way on the ingredients. If I look at what happens to an underdamped oscillator, then the best states turn out to be coherent states. Gaussians which are as round as a ground state. However, if I turn the environment down so its interaction is very weak and doesn't have high enough frequencies, then it turns out that it's the Hamiltonian of the system which decides what's most important. And then the eigenstates of energy are the best states. Right? So we know certain limits. Any other questions? So, brief summary of what decoherence does and what it doesn't do. Well, for now, what it does. Quantum theory can explain emergence of the classical principle of superposition loses its validity in open systems, systems interacting with the environment. Decoherence restricts stable states, states that can persist and therefore exist in the sense in which we normally think of this, to exceptional pointer states. They exist and evolve predictably, in spite of the fact that the system is immersed in the environment. Predictability is a strategy I've explained before, can sift through the Hilbert space and lead you to the corner which has that property of stability. So, environment-induced superselection is a process of selection of these preferred states. For macroscopic systems, decoherence can be exceedingly effective. It will enforce a ban on Schrödinger cat-like states. And it delineates an effective border that divides quantum from classical. So, you know, a point of view to a Bohr-head is possible, although he insisted on classicality being ab initio. Here you don't have to. Classicality comes out because of the. Now, I'm not happy with it. And so let's revisit foundations of quantum theory and try to understand how does that fit and to what extent does it fit. I'm going to list postulates basically as I've extracted them from a good textbook, Dirac. To me it's still the Bible. First two, states live in Hilbert space, evolutions are unitary. These two have to do with mathematics only. You know, if you know these, you can shuffle symbols, but there's no connection to real world. Number 3 begins to make that connection. It says immediate repetition of measurement yields the same outcome. Repeatability. I like it. Next to make more of that connection but get in trouble. Outcomes are restricted to orthonormal states, eigenstates of the measured observable. Now why should they? And in fact we know it's not always true. I mean, we can measure and come up with coherent states which are not observable, so there is no permission observable. And you also see just one outcome upon each run of the measurement. That's known as a collapse postulate. And number 5, probability is given by the square of the amplitude. Born's rule. That's crucial in interpreting experiments. I'm going to add one more which is not in Dirac, but we need it, and we use it, especially in quantum information. State of a composite system is a vector and the tensor product of